yourself. Well, first of all, thanks for inviting me. Thanks for inviting me back. I think it was either 2 or 3 years since I was last year, but it was before any data had been released from Gaia, so there's quite a lot has happened in that time, which I'm going to tell you a bit about. So I'm at the Royal Observatory in Edinburgh. I'm part of the Wide Field Astronomy Unit. We're a group of around 15 astronomers and software engineers who specialise in processing, archiving and curating data from some of the large telescope facilities around the world. So we're involved with UCURT, the UK Infrared Telescope, the VISTA Telescope, some of the next generation things coming down the line. The Large Synoptic Survey Telescope will be I think the UK Data Processing Centre for. But there's also 2.5 of us that work exclusively on Gaia.
2.5?
Yes, yeah, right down the middle. So this is what I've been doing full-time for about 5.5 years, so I thought I'd tell you a bit about some of the science that's coming from this, and also try and give you a broader picture of what's involved in operating a sensitive scientific instrument 1.5 million kilometres out in deep space. So this is Gaia. It's a European Space Agency mission. It's both the name of the mission and the space telescope itself that's being used to carry the mission out. So it's an effort to survey our galaxy, the Milky Way, in very fine detail.
Exactly 2 months.
So feel free to stop me and ask questions at any point. If I'm talking too fast, tell me to slow down. If I run over, tell me to shut up.
Lights on or off?
I guess off or dimmed might be better.
Either on or off.
I'm just going to set my clock running so I can sit. Okay, so the main goal of the Gaia mission is to measure the structure, composition and evolution of our galaxy, the Milky Way. So the Milky Way is a very complex system. There's lots of different processes that are all operating simultaneously. It contains a mixture of planets, stars, gas, dust and dark matter. These are all widely distributed spatially within the galaxy and in age. Everything's held together by the long-range attractive force of gravity that operates between everything that has mass. The gas experiences pressure forces as it collides and mixes. There's magnetic fields in there. And trying to kind of understand all of these different processes in one coherent picture, how they work together to build a galaxy like ours, is the overall scientific aim of Gaia. Along the way we'll also see pretty much every stage in the life cycle of stars, including some very short-lived phases that are hard to detect. We'll recalibrate the astronomical distance scale, to remeasure the size of the observable universe by making the first precise calibration of Cepheid variable stars. Other scientific goals, we'll make some new stringent tests of Einstein's theories of relativity. Pretty much every branch of modern astronomy will be touched one way or another. And Gaia is what's known as an astrometric satellite. Astrometry is a very ancient field within astronomy that's concerned with making very precise measurements of the positions of stars in the sky. And the point is that by repeatedly measuring the position of a star over time can reveal certain tiny motions that turn out to be crucial to understanding the nature of individual stars and populations of stars, and then the galaxy as a whole. Over the 5 years of the mission, we'll map the entire sky on average 70 times. Some bits will be revisited several hundred times, just the way the scanning pattern works out. We're aiming to measure the three-dimensional positions and motions of somewhere between 1 and 3 billion stars. We're about 1.3 currently. It's turning out that there's more stars out there than we really realise. It's only when you do a survey like Gaia that you find out how many there are. That's still only about 1% of all the stars in the galaxy. which is still a significant number of stars. And Gaia ultimately is an instrument for measuring very precise angular positions. It's really just a glorified angle measuring device, but it does this very precisely. The final end of mission precision that we're aiming for is an angular error of 20 microarc seconds. So an arc second is just an angle, a very small angle. There's about a million of them in one complete circle. A microarc second is 1/millionth of that. So 20 microarc seconds is about equivalent to the width of a human hair viewed from about 1,000 kilometers.
Oh, Jesus.
So it's very, by far the most accurate survey of its kind. We'll also discover tens of thousands of brown dwarfs, both free-floating and in multiple star systems. Hundreds of thousands of asteroids, mostly in the main belt between Mars and Jupiter. And we're hoping for around 10,000 extrasolar planets that are detected by a couple of different techniques. Gaia launched close to Christmas 2013 from Kourou in French Guyana. This is Soyuz rocket. Gaia's folded up in the upper stage here. This is what it looks like. The sun shield actually folds up like this, just in order to fit inside the fairing. Let's just play through the launch. It's a fairly quick journey to space. Within a few minutes, Gaia was put into a holding orbit around Earth at a couple of 100 kilometers altitude. The sun shield was deployed. Everybody breathed a sigh of relief when that mechanism worked. And then over about a month it transferred out to where it is now, which is a point called the second Lagrange point, which I'll explain a bit later. We're observing around 50 million stars per day. That's about 2 million during this talk. At times when the scan pattern of the satellite aligns with the Milky Way, we get about 250 million stars per day. So it's a huge volume of data. And it might seem that putting a sensitive telescope into space is a lot of effort to go to, but there's a lot of reasons why doing astronomy from space is attractive. Some more or less obvious than others. We have a very high, what we call observing efficiency from space. We can see the entire sky. You know, for any site on Earth, you'll see at most about, well, maybe half of the sky is for usable observations. We can also observe 24 hours a day. There's no night as such up there, or daytime. Whereas obviously telescopes on the ground, you have to close them up during the day. There's no atmosphere in the way, which is a great help. The atmosphere introduces various effects that spoil precise measurements of the positions of stars. Space, the second Lagrange point in particular, is a very stable environment with very low temperature fluctuations, and there's no gravity, so the telescope doesn't flex as it moves like telescopes on the ground do. There's also obviously many challenges. We have a very low bandwidth for sending data back, only around 1 megabyte per second in practice. The data has to be highly compressed. That's a very narrow pipeline to send it all back to. We get about 50 gigabytes per day, which compared to things like the Large Hadron Collider is very little data. But it's very complex and takes some quite sophisticated processing. There's no servicing or refueling. Exhausting the propellant is often the thing that ends the lifetime of missions like this. And we can't replace parts that break, and some parts have already broken, as you'll see. We're constantly bombarded by cosmic radiation from sources in the galaxy and from the sun. Actually turns out to be a big source of this. And we're also constantly bombarded by micrometeorites, which we can detect from the way they knock the satellite, as we'll see a bit later. So Gaia is really the update of the Hipparcos mission, which is the only other mission like this that ever flown. Hipparchus flew for 4 years in the early 90s and just went dead one day in 93, and no one really knows what happened to it. I should say Hipparchus and Gaia are both European missions, and it's one of the branches of astronomy that Europe really leads the field in. NASA doesn't really do anything similar to this. Just to give you a bit of a grounder in astrometry and what it is we're actually trying to measure. So we talk of measuring 6 dimensions for each star, 3 dimensions of position and 3 dimensions of motion. So what we can actually observe, the first couple of dimensions are simply the angular position of a star on the sky, analogous to latitude and longitude on the Earth's surface. We're essentially seeing 3-dimensional structure in projection on the sky. Next couple of dimensions of the proper motion refers to the gradual movement of stars across the sky. Stars in the vicinity of the Sun tend to move anywhere from tens to hundreds of kilometers per second relative to the Sun, and over time we can perceive that motion with precise enough measurements. This is one example here. This isn't Gaia data, this is from the Liverpool telescope, I think, but this is 2 images taken 18 months apart, targeting this white dwarf star. This is moving around 30 kilometers per second relative to the Sun, so you can actually see stars moving like this. The 5th dimension is an interesting one. This is the parallax, which is what gives us a measure of the distance to each star. And the way this works is by triangulation. So you can imagine from the Earth here measuring the direction towards a particular star, this is it on the right here, and repeating the measurement 6 months later, and because the star is at a finite distance, the direction that we perceive towards the star is slightly different. If I flip back and forth between the two, you can see the effect that this actually, how this manifests in an image of the star. So we measure this small displacement and draw a triangle like this. What we measure here is this angle P, the parallax. We know the length of this axis, it's simply the radius of Earth's orbit around the Sun, and that allows us to use a bit of trigonometry to get the length of this axis, which is the distance to the star. So this is the parallax method. It holds a special place in astronomy because it's the only means to directly measure the distance to anything in the night sky, really, geometrically, in a way that doesn't make any assumptions about the object that's being studied, such as its physical size or its motion or something. The parallax angles that we measure are tiny. Even the most nearby stars have parallaxes of around 1 arcsecond, which coincidentally is about the same scale as the blurring effect of the Earth's atmosphere. So a bit of a coincidence of nature. If the atmosphere was slightly thicker and the seeing was worse, it's possible that we would not have ever actually been able to detect parallaxes from the ground, and we wouldn't have known the true scale of the galaxy until the 90s when Hipparchus flew. We need about 18 months of data to distinguish the motion, the proper motion from the parallax. Both of these affect the observed position of the star, and it takes at least 1, 2, 3 observations in order to untangle the two, which is 18 months. I put relative versus absolute parallax here. This is somewhat technical, but from the ground, by making observations along one line of sight, the only way that we can measure these small angles is by measuring the position of this star relative to the background stars, which are at a larger distance. But they're not at infinite distance, and all of these reference stars will have small parallaxes. So what we end up measuring is the parallax of this star relative to these background stars, and correcting for that is very tricky. The way to get around this is by measuring the angular position of this star relative to stars along a completely different line of sight, along which the parallax motion is out of phase. and that simply can't be done from the Earth's surface because it forces you to look through a large volume of atmosphere, which is why astrometry is done from space, Hipparchus and Gaia. And so all of these effects and others combine to make the observed position of a star, how it changes over time, really quite complex. Binary stars will kind of orbit around each other like this as they move across the sky. Large masses in the solar system, the Sun and Jupiter in particular, actually deflect the light slightly due to some general relativistic effects. And all of these, this is just one somewhat hypothetical example of how a star can move. So you can imagine in dense regions where there's stars going in all different directions like this, actually cross-matching them from one observation to the next and figuring out which was which is quite a big challenge. Fortunately, those are quite rare cases, but it's still something that we have to deal with. And finally, the sixth dimension is the motion along the line of sight, which is the only one that we can't measure by making repeated positional measurements. Gaia has to use different instrumentation to get this. And the way we do that is by passing the light from each star through a spectrograph to disperse it into the spectrum. This is one example of from Gaia here. So on this axis is the wavelength from blue to red. This is the intensity, so you can see that the star light has a kind of continuum level here, and then there's these deep features which correspond to particular spectral lines of elements that exist in the atmosphere of the star. These tell us a lot of things. Mainly what they tell us is the radial velocity along the line of sight, because if a star is moving towards us, these lines are all shifted to slightly bluer wavelengths, and if the star is moving away from us, these lines are all shifted to slightly redder wavelengths, and that shift tells us the speed. But the lines also tell us a lot of other things. The depth and the detailed shape of these tell us the chemical composition, the temperature, the strength of the force of gravity at the surface of the star, whether stars are rotating, all manner of additional things. Spectral lines are really kind of like the fingerprint of a star. So just going into the design of the Gaia satellite a little bit more, this is a scale model here, 1 to 50. So the real thing is about 10 meters across. The payload housing here is about 2 or 3 meters wide. It's actually got 2 telescopes rather than one, that both look out from these 2 rectangular apertures here. Okay, and these look in 2 different directions simultaneously, separated by about 106 degrees. And the satellite sits out in space, keeps this sun shield at an angle of 45 degrees to the sun at all times, and just slowly spins like this once every 6 hours. And it gradually sweeps those 2 fields of view across the sky like this. And what that allows us to do is, by simultaneously measuring the positions of stars along this line of sight and that line of sight, it gives us very precise angular separation between the stars. And the point there is that as the satellite spins and processes and gradually scans the entire sky, over time it'll link every star to many other stars, many relative angular measurements of the positions of stars, which can be solved for simultaneously in one big triangulation, which gives the positions, motions and distances of all the stars simultaneously.
Is 106 degrees significant? Was that just chosen, or is there a reason for it?
There are 10, yes, no, it's very careful. It's one of the main parameters for the entire satellite design, actually. In order to make the parallax measurements more absolute, to free them from any dependence on the parallaxes of the background stars on the line of sight. The angle needs to be about 90 degrees, but 90 degrees or any regular division of the circle is bad for other reasons, in that as the satellite scans, we need to link each star to many other stars, and say the two telescopes are at 90 degrees, we'd initially link this star with stars along that line of sight. When the satellite turned, it would link these ones and those ones, turn again, it would link those ones and those ones, and then turn again, it would link that one back with the original one. Whereas if it's some funny figure like 106, as we go around, it sort of...
rotational symmetry.
Yeah, exactly. This technique requires accurate knowledge of where Gaia is to within around 1 metre. Well, we track it from Earth to within around 1 metre by a combination of optical tracking and radio measurements. This is a clip of how the scanning pattern on the sky actually looks. This is just the right ascension and declination coordinates. The blue line is the ecliptic plane. This is the sun as it moves through. This is the spin axis of the satellite, and these two blue bits, which will shortly start moving, are the directions that the two telescopes are looking along. So this is within the first day of the mission. Things speed up a bit. Okay, that's 2 days in. Then quickly, let's see, we start to fill out the entire sky. So this is a few months in.
Is the colour representing the...
Colour represents the number of times that each bit of sky has been revisited. So you can see some bits are revisited far more than others. Okay. So yeah, I'll kind of pause it there. But if you can take a kind of mental snapshot of that scan pattern, because it'll come back up a bit later. So just looking at the guts of the instruments on board, so that the light from the two telescopes is actually merged and projected onto the same array of detectors called the focal plane array instruments. This is how they're laid out inside the telescope. It's actually pretty much 1-to-1 scale. So there's 106 CCDs, about 1 billion pixels in total. And these are split among several instruments that do slightly different things. Because the satellite continually scans and doesn't stop to take images, what happens is that stars drift across the focal plane like this, from left to right, over about a minute, and they hit, they travel in straight lines like this, and they hit a series of instruments. The first two strips of detectors here, these each have only light from one of the two fields of view coming through them, and they, in real time on board, detect stars and predict their motion over the rest of the instruments. And that's important because we have to be able to tell which of the two telescopes a given star was detected in. And then once they've moved off these two star mapper instruments, they hit the big green blob here, which is the astrometric field, which is where we make the astrometric measurements, the position of each star. The two strips here are the blue and the red photometers, which are where we measure the brightness of each star in blue and red light. The light is passed through prisms, which disperses it slightly. So instead of looking like stars here, they're actually spread out slightly into a kind of small rainbow. The last block here is the radial velocity spectrograph. The light that hits this is passed through a diffraction grating, and this is where we measure the spectral lines. This is what the final few mirrors look like, the diffraction grating, the prisms here. That's the real thing, built by Airbus. There's a couple of other instruments here that are used to measure the focus of the telescope. This is what stars actually look like through the Gaia optics, through one telescope and the other. This pattern, this shape, changes over time, changes with the colour of stars and stuff. My entire job is to measure that and map it out and model it mathematically. When we come to measuring the positions of stars, we fit this template to the observation, and by doing that we can measure the positions to within about a hundredth to a thousandth of a pixel in one observation. This is a visualization of what happens when we scan through a very dense region of the sky. So each one of these points is a star that's been detected by Gaia. You can see the 7 rows here, or the 7 rows of CCDs as it scans across Omega Cen. This is the globular cluster, Omega Centauri. It's the densest part of the sky that Gaia ever observes. The onboard object detection is tuned to detect stars, but anything that's sufficiently point-like can also trigger it. And we indirectly detect all kinds of other things. This is a whole bunch of blue points, each of which is a blob that Gaia has detected. You can see they trace out this funny pattern. Does anybody recognise this?
It's a double helix.
Exactly, yeah. So this is what happens when Gaia scans through something that's, some extended shape like the Cat-Eye Nebula. Tight pockets of gas in this expanding shell have triggered the object detection. So you can kind of think when, over time, as Gaia scans this multiple times, we might be able to measure the expansion of the nebula precisely.
What's the faintest magnitude of star that can...
So we go down to around 21/21st magnitude in the Gaia G band, which is very broad. So it's actually not very deep compared to things like Hubble. And this is partly why. So this is a lot of the major telescopes, they're collecting areas. So what have we got? Keck, there's the 2 Keck telescopes. That is Hubble down there, about 1.2 meters across. There's Gaia. The apertures, the main mirrors are about 1 meter by 60 centimeters or something. So they're not very big, and it's with the continuous scan we get a fixed integration time of about 4.5 seconds, which limits the magnitude that we can see to quite significantly. So, but there's still an awful lot in the sky down to 21st magnitude. So the guiding principle of the entire satellite construction and design was to make a very stable platform from which to make precise observations. This is a kind of expanded view of the whole thing. The top bit is what's known as the thermal tent. This is just an insulating structure that sits over the payload and all the scientific instruments, and aims to keep it at a uniform temperature, protect it from meteorites to some extent. Next bit down is the optical bench where all the instruments are housed. This is based on a large donut of silicon carbide, a very hard ceramic that's very resistant to thermomechanical flexing. There's 11 mirrors that are attached to this. These are the primary mirrors of the 2 main telescopes. The light comes in like this, bounces off there, bounces off a mirror here, bounces off that mirror, hits a mirror here, off that one, then onto the focal plane. It's like that for each of the 2 telescopes. So the beam is folded back and forth. It gives us a 35 meter focal length in a structure about 3 meters across. This is the service module where all of the electronics are housed. The idea of keeping them separate is to insulate the optical bench from any heat that's given off by the electronics. There's a lot that's done on board. And we can actually detect things like when we scan through more dense regions of the sky, the onboard object detection is working harder, it heats up, and that can cause that silicon carbide torus to flex a little, which slightly changes the positions of stars. This is a set of micro thrusters which are used to maintain the orientation of the satellite. Because of the requirements for extreme stability, there's only two moving parts on the entire thing. One of them is the valves in these thrusters. The other one is a focus mechanism behind one of the mirrors here. Those are the only two bits that move. Instead of a steerable dish, we have a phased array antenna, which is just a particular type of antenna that allows you to broadcast in different directions without moving anything. Most other probes will have some kind of large dish that swivels like this, but the risk of that destabilizing the telescope is too high. And lastly, this is the sun shield, this big piece, and there's solar panels on this side of it, and the antenna and everything sits here, and it keeps this pointed back towards the sun and the earth constantly. So I mentioned Gaia's in space. It's not in orbit around Earth like Hubble is, like Hipparcos was. It's actually further out, about 1.5 million kilometers, about 4 times further out than the Moon, at a point in the solar system called L2, or the second Lagrange point. This is a gravitationally stable, gravitationally neutral point in the solar system that's quite popular now for placing telescopes. It's thermally stable. The illumination from the sun is constant, whereas if you're going around the Earth, you're constantly being eclipsed, which is quite a large temperature shock. It performs a Lissajous orbit here, which is like a figure of 8 around this L2 point, and it's tracked to within 1 meter from Earth by a network of optical telescopes and radar ranging. This is Gaia here in the optical tracking. Shortly after it was launched, it was detected by the Minor Planet Center, and it, for about 14 hours existed as a potentially hazardous asteroid until they realized what it was. We maintain pretty much constant communication with it via the 3 deep space antennae that ESA operate. So these are in Australia, Spain and Argentina, so roughly a third of the way around the Earth, so that as the Earth rotates, as one is going over the horizon, another one's coming up, so that they can hand over the connection and we continually download.
Are they dedicated to Gaia?
No, they're not. They're not. So they do other things as well, and I'll tell you later. But NASA requisitioned them earlier this year for the InSight mission launch. But Gaia has some ability to buffer data on board for periods when it's out of contact. So short outages are not too bad. The data processing is done all around Europe, 6 big processing centres. 2 main aims. One is to, in real time, monitor the health of the satellite, make sure it's still meeting the scientific requirements. And every couple of years we have a big cyclic processing drive to produce the data products that we release. All of the software that we write in Edinburgh is run on the Mare Nostrum supercomputer in Barcelona. It's housed in this glass box in the grand hall of a deconsecrated 19th century chapel. This is it. It featured in a Dan Brown novel from last year. I haven't read it. I believe it's called Origin or something like that. So there's a lot of challenges that we have to deal with in operating Gaia. Just to run through a few, the basic angle between the 2 telescopes has to be fixed, or as close as possible to being fixed, because any variations can have a detrimental impact on the data. It turns out that angle is varying slightly due to various reasons. as the telescope turns, different bits of it are heated by the sun more than others, and that slight temperature fluctuation causes some kind of breathing of the telescope structure. For the first few years of the mission, we were getting ice condensing on the main mirrors. It turns out some component of the spacecraft was outgassing water vapour, which was then recondensing. Periodically, we had to heat up the mirrors. This was anticipated to some extent, and heaters were built into some of the mirrors. So these were turned on to melt the ice off. But that's a big thermal shock that it takes a couple of weeks to recover from. We had competition for ground station time in 2018. This was a Mars launch window, and NASA's InSight mission was launched back in May. And while it was on the way out to Mars, they were using some of our ground station to contact it. It actually lands on Mars on Monday. I think the landing is going to be live. So.
Tasked with looking at it again.
I don't know actually. That's a good point. But I think you can actually watch it live online, so it might be worth checking out. We're constantly bombarded by cosmic radiation, high energy particles that either whiz straight through the detectors or, even worse, embed in them. This is kind of what it looks like. This is real raw Gaia data actually. The onboard object detection allows us to transmit back to Earth only 12 by 18 pixel windows around each star. So this is what stars actually look like. That's the star there. That is a cosmic ray. This is a high energy particle that's pinged through the detector coincidentally at the same time we were observing the star. These have a lot of different origins, sources in the galaxy, sources outside the galaxy. The sun is a big source as well. Whenever there's a big solar flare that hits Gaia, we get swamped with these, which can cause various problems. There were a couple of big solar flares in September last year. These are the biggest ones of the mission so far. Accumulated about 1.5 years worth of radiation damage in 3 days. But we're still way below pre-mission forecasts because the sun has been fairly quiet. But any large solar flare that hits Gaia has usually hit the Earth about 8 hours previously. This is what happens. So whenever I see something like this in the news, I panic that Gaia's going to get fried. One big solar flare is all it would take to destroy the spacecraft. But we've been lucky so far. From time to time, Gaia enters what's known as safe mode. We all do this. This is when it's detected some major fault on board and put itself into a kind of hibernation, and the mission operators have to try and figure out what's happened. We've only really had 2 of these in the mission so far, one in June last year that only lasted a couple of days. This was caused by a bug in the onboard software. Following the routine firing of one of the thrusters, some sensor failed, and it caused Gaia to think the temperature was continually rising due to some fault in the thruster, so it shut everything off and went into safe mode. But there was actually no fault at all, and the software has been updated to fix that. In February this year, on the other hand, we had a very big safe mode that lasted for 10 days. The mission operators turn everything back on one system at a time to try and figure out carefully what's failed. In this case, one of the 2 transponders had died. The transponder is a part of the radio communication system. It's required to send anything back to Earth. The one that was being used had just died. So we're now operating on the backup transponder, so it's a single point of failure risk now. Pretty much as soon as Gaia was turned on, it was clear that there was a large amount of stray light coming through the optics somehow. A lot more than was predicted, and a lot more than what should have been there given the design of the optics. This is an image of the focal plane array showing the straight light over a period of 1 revolution. You can see there's this huge blob up here and a lot of features that zip across it like this. Large straight light levels are not a catastrophe, but they make faint stars harder to see, so it limits the detection ability of Gaia. Eventually we figured out that this had 2 main causes. One was that along the edge of the sun shield there was a cut edge of this multi-layer insulation, and some fibres remained sticking out like this, and the sunlight was striking these and then getting scattered down into the telescope optics. This was to some extent anticipated before launch, and the decision was made not to tape over those seams because of the risk that the tape itself would get dislodged and end up falling into the optics. We've also since discovered that there are rogue light paths through the optical system. There's a kind of third field of view between the two, and when anything bright enters that, we get a lot of stray light. With 11 mirrors and no real baffling, it's hard to avoid things like that. What's happened here? Oh yeah, okay. So we get, as part of the data processing, we measure the orientation of the satellite very precisely over time, and we detect very small continual disturbances and knocks. This plot here shows over a period of about 15 minutes the rotation rate of the satellite on this axis. You can see it's kind of stable, and then all of a sudden there's this large ding, and the attitude control system takes a bit of time to recover from that. This is what happens when a meteorite hits the satellite. These happen several times a day. Some of the larger ones we can actually tell where they came from the attitude control that's necessary to recover the orientation. This is another example here, which turned out to be a Perseid meteor. In October, the Draconis meteor shower was actually predicted to pass directly through the volume of space where Gaia is, and there was a significant risk of Gaia being hit by lots of these. So for 2 days, they switched off the instruments and turned the satellite to face the sun shield towards the meteor stream, and 2 days later we all crossed our fingers and they turned it back on, and it was fine. We were fortunate and hadn't been hit by anything. There's also thermomechanical, what we refer to as microclanks, which are just these thermomechanical breathing. All of this has to be dealt with. Just to wrap up the first section and move on to some science. So the overall mission status, everything pretty much is working well. Attitude and orbit control is good. We've got propellant until about 2023, so we're hoping for mission extensions until then.
Is it like quite a few other missions that if you're really careful with your propellant, you can maybe spin it out a bit more?
Yeah, that's the propellant is a hard deadline. If that's assuming we don't get hit by a meteorite or a solar flare before then. We've lost one transponder. All of the electronics and detectors for the science instruments are working. As of last Sunday, the amount of data we've collected, we've got 1.1 trillion astrometric measurements of stars. So with 1 trillion observations, this becomes quite an interesting data science challenge. Any freak event that happens once in a million will happen a million times. The rare events exist in great abundance, and we have to be able to tell the 1 in a million freak artifacts in the data processing from the 1 in a million real astrophysically interesting transient events. We've got 2 data releases in the bag already, one from 2016 and one which I'll mainly talk about now from earlier this year, which is when things really got interesting. So the first data release was 14th of September 2016. Made the news pretty much all the way around the world. This is just a selection. Even made it to the China Daily. The Mail's in there somewhere, yeah, and China Daily. Data release 2, on the other hand, didn't really make any kind of splash at all. ESA made a bizarre decision to release it at a press event at the Berlin Air Show, and at the last minute piggybacked onto it a bunch of other ESA stuff about the Sentinel launch, so it didn't really appear in the news at all, unfortunately. But this is the headline figure that was released with the catalogue. This is a summary of what it contains. So we've got about 1.7 billion positions and brightnesses of stars. About 1.3 billion of those, in addition to the position, we've got the proper motion and the parallax. So that's about a factor 10,000 larger than the nearest comparable survey. A few interesting things in here. There's about 500,000 variable stars. That blob there is about 14,000 asteroids in the solar system. The data is all freely available online through a database system at the Gaia archive here. Documentation and papers and everything are here. I'll put these back up at the end. Yeah, so I'm going to spend the last 15-20 minutes just showing you some of the science that's come out of it so far. This is from data release 1. This is the density of stars in the Gaia sky, projected in galactic coordinates. So along the equator here is the Milky Way, the plane of the galaxy. You can see all these dark dust lanes where the stars are obscured. This overall swirly pattern that you can see, if you think back to the scanning pattern that I showed you previously, this is an artifact that remains in the catalogue from the scanning. This is the large and the small Magellanic Cloud. You can't see them from the northern hemisphere, but if you're ever on holidays, when you're in South Africa, David, you might be able to see these. A few other things in here. This bright blob superimposed on the small Magellanic Cloud is a globular cluster, 47 Tuc. Omega Cen is another globular cluster, that's up there. The Orion dust clouds are here. We've got Andromeda, Sculptor and Fornax. So as well as stars in our galaxy, we're getting bright stars in some of the nearby galaxies in the local universe. Loads of stars in the Magellanic Cloud, actually. And this is what it looks like in data release 2. So you can see a lot of these artifacts are gone now. The sky is much more uniformly mapped. I think, yeah, this is the same thing in colour. So with data release 2 we've got colour now. I have some posters of this to give away at the end, so grab one. So there's a lot of good stuff in there. Okay, I'll leave that one up just while I talk about the other slide. So some of the improvements that have been made with the second data release, our angular resolution is much better, so we can distinguish stars that are about 0.4 of an arcsecond apart. That's roughly equivalent to what Hubble telescope can do, but we're all sky now. So it's mapped like the entire sky with the resolution of the Hubble telescope. We're pretty much complete from 12th to 17th magnitude, which means everything that shines within those 5 orders of magnitude is mapped. We lose some of the faint stars because of issues with low signal to noise and resource limitations on the satellite. The fainter ones are the ones that are not broadcast back to Earth if there's any limit. The bright ones, anything you can see with the naked eye, isn't in Gaia yet. We have problems with saturation in the detectors, which we'll deal with in time, but at this point those stars are still missing. Yeah, let's skip across that. So some of the science that's come out. This is the HR diagram, Hertzsprung-Russell diagram for the solar neighbourhood stars in Gaia DR2. So on this axis we have the colour of stars from blue to red, equivalently from hot to cooler surface temperatures. This axis is the intrinsic luminosity from bright stars down to faint stars. You can see that the majority of stars lie along this tight sequence here. This is the main sequence where stars are powered by nuclear fusion of hydrogen in their cores. Our sun is somewhere around here. The top end of this, the stars have shorter lifetimes, and when they exhaust their central hydrogen reserves, they turn off at this giant branch. And then eventually, once they shed their outer layers and briefly turn into planetary nebulae, they move like this and end up in the white dwarf region down here. So, having worked on white dwarfs during my thesis, this is an amazing thing to see. There's a huge number of stars here. This is a zoom in on it. There are various completely unexpected bits of astronomy that immediately showed up in this, and one is that the white dwarf sequence kind of splits into two. You can see there's two main streaks there, which no one was really expecting, and we spent some time trying to figure out what was causing that. We think it's that the stars in this lower branch here have formed from the merger of two stars, so they're more massive and fainter than other white dwarfs of the same colour. That's interesting because that implies our understanding of how populations of stars in the galaxy have evolved. Needs to be revised slightly. This is the HR diagram for some globular clusters. This is just the top end of the main sequence. This is the subgiant branch, then the red giant branch here. This is the horizontal branch where the stars are burning helium in their cores rather than hydrogen. And this is coloured according to the metallicity of the globular cluster, or the fraction of material heavier than hydrogen and helium. So you can see a strong metallicity dependency here, particularly in the horizontal branch. This is interesting to the globular cluster specialists. Other end of the scale, these are two nearby open clusters of stars, very, very young, more sparsely populated star clusters. Their main sequences, this is the Hyades and Praesepe completely superimposed. You can see how thin this main sequence is. The remaining scatter here is due to the errors in the distances to the stars, not in intrinsic differences in brightness. These points that are all about half a magnitude brighter are unresolved binary stars that are about twice as bright as they should be, because there's actually two stars there. Looking at the motions of stars now, this is the disk of the galaxy, looking down onto it from above. In each diagram, the centre of the galaxy is about here. We're out here at this black blob, and the stars rotate around the galaxy in this kind of direction. But what's shown on this side is coloured according to the motion of stars inward and outward. So you can see in red here, these stars are moving slightly towards the centre of the galaxy. These blue regions are moving slightly towards the outskirts of the galaxy. Similar thing here, but now it's coloured according to the rotational motion. So these red blobs are rotating slightly faster, these blue blobs are rotating slightly slower. Really the interesting thing here is to see the rich structure and complexity that's present. It was never really anticipated that the motions of stars in the galaxy would be as complex as this. This is all due to influence of large gravitating structures like the spiral arms and the bar at the centre of the galaxy. This is the Large Magellanic Cloud here. We've measured hundreds of thousands of stars in the Magellanic Cloud, and you can see its rotation now in the proper motions of those stars. So these small arrows here indicate the average proper motions of stars along at each point. This is the rotation curve here from the centre of the Magellanic Cloud to the edge. This is the rate at which it's rotating as you move further away from the centre. So you can see initially it's the rotation increases and then it flattens off and the outer parts rotate kind of like a solid disk. This is interesting because rotation curves like this are the sort of smoking gun of dark matter in galaxies. Pleiades is an interesting case. So Pleiades is a very nearby young open cluster of stars. Clusters of stars are useful to astronomers because stars are formed at the same time from the same mix of material. They're all at the same distance, so they're good testing grounds for our theories of stellar evolution. And for the Pleiades, which should be well understood, there is for a long time a disagreement between the distance estimates between methods that require an understanding of stellar evolution and distances estimated from Hipparcos using the trigonometric parallax method. These are some of the estimates for the distance here. This is the distance on this scale. Isochrone fitting is where we measure the main sequence and then fit models to this to try and see how bright it intrinsically is. Some analysis of binary orbits of binary stars in the Pleiades can give us another way to estimate the distance. There's a few other things here, but these all kind of agree on a distance of around 136 parsecs or something, whereas Hipparcos put it about 10% lower, about 120 parsecs, which is a big deal because that is a significant difference. If Hipparcos is right and these other methods are wrong, then we really don't know what we're doing when it comes to modelling stars. So everyone was really interested to see what Gaia would have to say about this. And well, essentially this is Gaia here, right smack bang in the middle of all these more traditional methods. So it certainly is looking like something went wrong with the Hipparcos distances for the Pleiades, which we have some ideas what that might be, but because Hipparcos uses the same observing principles as Gaia, there's a drive to try and figure out exactly what happened. This was a paper that I picked out that was quite interesting, based on data release 1. So geologists will tell you that if you look at the fossil records, there's a number of mass extinctions on Earth that seem to have a frequency of about 30 million years. If you kind of squint when you're looking at the graphs. 30 million years is also roughly the time scale on which the sun goes up and down through the disk of the galaxy as it rotates, as it orbits around the centre. So there was this idea that maybe in the plane of the galaxy there's some thin, dense, dark matter disk that whenever the sun passes through it, it disturbs the comets that exist on the outskirts of the solar system, and that knocks some into the inner solar system, which then hit Earth. So a little tenuous, really. But one thing we can do with the Gaia data, because we have the three-dimensional motions of stars, we can actually wind the clock back and forwards and see if any nearby stars happen to pass very close to the sun. Because these could impart a similar kind of kick to the comets. And so that's what Corin Baylor-Jones did here. This is the main result from the paper. So each one of these blobs is a star. On this axis, the perihelion distance, this is the closest approach that each star makes to the sun. And on this axis is the time of that closest approach, with 0 today, here, going from about 10 million years in the past to 15 million years in the future. And you can see these, for example, this star passes about 3.5 parsecs from the sun in about 5 million years. Large spread of points up here, but then there's this one.
It's not Barnard's star.
That it's not Barnard's star, but it's one that, I forget the name, but it's one that was always known to pass close to the sun. But Gaia has it passing a lot closer. Within the Oort cloud of comets. So when this one passes, it will impart a huge kick to the cometary bodies. But it's 1.3 million years in the future. So
We don't know.
What type of star is that?
I think it's a K dwarf. Can't remember. I'm just going to skip on a bit because we're running out of time a little. This was an interesting one. So in Gaia DR1, this group, these are in Cambridge, detected 2 new star clusters in the sky, which are large and really should have been discovered already, but they haven't been because they're right next to Sirius. Okay, so this is an image taken by an amateur astronomer showing where one of the star clusters is. It's hard to make anything similar to this with the Gaia data because it doesn't take conventional images like this. So this is Sirius masked off with I think just an actual piece of card that he's stuck over the telescope aperture, showing where the star cluster is. It's not been detected before now because the majority of telescopes don't like to point at something as bright as Sirius, and even if they did, this would all be really swamped by straight light. So if you're an amateur astronomer, this would be quite an interesting thing to try and image. Okay, we're close to an hour, so yeah, let's just look to the future a little. So the end of the 5-year nominal mission of Gaia is in summer next year. We a few weeks ago had a 2-year mission extension confirmed, so we'll be going for at least 2 more years after that. We're hoping for a 5-year extension, which would take us to when the propellant runs out. So we really can't go any further than that. Each extension has to be justified scientifically. So the reason for wanting to extend Gaia, there's a few good reasons. With more time, we accumulate more observations of each star. So with 10 years rather than 5 years, we'll have twice as many observations. That means the accuracy on the positions of stars will be around a factor of 1.4 better. The proper motions scale a bit better than that. The accuracies will be about a factor of 2.8 better. But the main reason was that it gives us a much better baseline for discovering exoplanets. So it means with 10 years we can potentially discover exoplanets that are further out from their star and have longer orbits. Whatever happens, summer 2019 at the end of the nominal mission, we've got a couple of big events coming up. Gaia is due to be eclipsed by the Earth on the orbit that it's in currently, and we have to make a large orbital maneuver to correct for that. And we'll also be, for various reasons, reversing the spin direction for a year. So Gaia is currently spinning like that, we'll be spinning like that for a year, and go back to normal. And over time we're continually improving the data processing. There's always new things we're learning about how the instruments work. Third data release is coming out in early 2021. We've been working hard on this all of this year. It seems like a very long way off to 2021. But there's a lot of new modules that are coming online this time for the first time. Multiple star systems, extended objects like galaxies. We're hoping to detect new asteroids in the solar system. Up till now we've only been able to make observations of already known asteroids. Each data release will add certain new data products as well as updating all of the existing ones. We're also working on a proposal for the follow-up mission to Gaia. So Gaia observes in the optical light, and its big blind spot is in the plane of the galaxy where the dust lanes obscure stars close to the centre of the galaxy. So there's this proposal called Gaia Near Infrared, which is essentially to do exactly the same thing, just with infrared detectors rather than optical detectors, and that infrared light will allow us to punch through the dust and do essentially the same thing, just towards the centre of the galaxy. Problem with that is that the necessary CCD detectors don't exist yet, so ESA is having to fund the technology development for these. It's one of the ways in which investment in space technology makes its way back into society. And I'll just leave this up. This is some further reading if you're interested. This is an interesting review by Michael Perryman, who is the original proposer of Gaia. All of the Gaia data and documentation and everything is freely available online. If you've got a Oculus Rift, then this Gaia Sky application is a really good visualization. You can fly through the galaxy in 3D. And that's it, so I'll leave that there. Thank you.
Absolutely, thanks. Just a stunning mission. Any questions for them?
Yeah, I've got a few.
I noticed looking at the Gaia data, everything's in terms of epoch G2015.5,
Yeah.
which is a pain in the butt when you're trying to match things against the star chart of G2000 epoch. Is it?
Well, why is that?
There's no built-in calculator.
No, the reason for that is that 2015.5 is halfway, so that data release 2 is based on 22 months of data. 2015 and a half is right in the middle of that, which is the point at which the positions will be the most accurate. If you can imagine proper motion correcting the positions of stars to 2000 or something, then uncertainty grows. So that will probably always change with each data release.
I was wondering how you handle errors. So, like, you know, like cosmic rays, or like if you kind of, like basically anything. Like, do you ignore the data? Do you ignore the data, or do you kind of handle it when it comes to the ground?
Yeah, well, we have to deal with all that kind of stuff in on-ground processing of the data. So cosmic rays, we run a sort of source detector over the data, which can tell if a particular source is a star or a cosmic ray. It's relatively easy to tell things like those apart. Cosmic rays are very point-sharp, point-like objects. We also get all kinds of cosmetic defects, hot columns, cold columns, dead pixels. There's all kinds of responses in the detectors that we have to measure and model so that they can be subtracted from the scientific data.
Is there any way to differentiate those from, say, like a supernova that went off?
Well, this is the big challenge for the sort of data science challenge for Gaia. Cosmic rays, yes, we can tell that they're not stars for various reasons. Each observation we have 9 images like that because there are 9 CCDs that the star will pass across. Cosmic rays will only hit 1,
Right.
whereas a supernova will be...
Okay, so like because they kind of move across those cosmic rays, just kind of stay.
Yeah, they just punch through the detector and it will just... you would never get the same cosmic ray affecting each of the 9 observations. So that's one way. Error, we have to really accurately measure, quantify and account for a lot of sources of error in the catalogue, in the data. And right from the initial stages, from the raw pixels. So we do a lot of that.
Discovery of new galaxies. I've reading this week that a new galaxy, faint galaxy, dwarf galaxy close to the Milky Way had been discovered just behind the bulge of our galaxy.
Right.
And that there's a lot of Gaia input into that. Do you know anything about that?
It sounds about right. I struggle to keep up with all of the science
just
results that
released
are coming
this
out,
week,
but that sounds very plausible.
Right, well, I'll check that up myself. And the other thing I was interested in is this figure 8 orbit that it does around the Lagrangian point. Is that due to perturbations by the moon? As the moon goes around the Earth?
I don't think so, but
Because I remember some of the other
to be honest.
Lagrangian-based spacecraft kind of wobbled round and round like that. And I often wonder
Is it not just because the L2 point isn't a stable gravitational point in the way that L3 or L5 are?
Oh, right.
It's actually if you were set exactly on L2, you would drift off, as opposed to like L3 where you get pulled in. So you have to orbit the imaginary mass
I see.
of L2.
And the other curiosity I had was, what about nuisance objects that would get in the way, like the planet Jupiter? I mean, how does Gaia actually cope with that? Does it have a mechanism of shielding it out, or does it cope with it?
It has no mechanism to shield it out. The particular scanning that Gaia does is that scan lore is tuned to narrowly avoid Jupiter as much as possible. But having said that, even if it appears close to the field of view, the stray light from it can be very significant. But one of the bits of science that we're aiming to do is to look at stars very close to the limb of Jupiter and measure their deflection due to the gravitational bending of the light. So we are about 14 times over the mission. We'll actually scan straight across Jupiter, looking for those stars very close to the limb that are about an arc second or two from the limb of Jupiter.
How does it see Jupiter? Because does the data, like, when it hits the sensors, does it create a point of data, or is it a picture?
It swamps the detectors, and the onboard object detection goes crazy. So it assigns lots of
like similar to that cat-eye nebula.
Exactly, yeah. So anything that's extended or fuzzy can cause the object detection to go haywire. And one of the hardest things in the data processing is detecting those spurious observations and discarding them.
How much is done on the satellite versus on the ground? Like, I imagine it would make more sense to just kind of send dumb data to Earth, or would it be too much?
It would be far too much. Yeah, the whole point of the object detection is that it allows us to, for each star, we cut out an 18 by 12 pixel window and send that back. And for the vast majority, instead of sending back two-dimensional 18 by 12, they're actually collapsed along one dimension, and we just get a one-dimensional 18 pixel scan through the star.
Right.
Because for the astrometry method that we're using, we only have to measure accurately the position of the star along the scanning direction. The position perpendicular to the scanning direction is a lot less important.
Yeah.
So for the great majority of the stars that we observe, we get 12 pixels in a one-dimensional scan.
Yeah.
So there's not much to see, is the thing.
You said that the current data is up to starts magnitude 12, and you think you might have a way of getting the brighter stars.
Yeah.
Is that something done in the data processing, or is it something you're going to have to change on Gaia?
So we can observe up to about third magnitude in Gaia. The problem is that the scanning, because it's a continual scan, the star images take 4 seconds to drift across each detector, which fixes the integration time at 4 seconds. So that's okay for the faint objects, but for very bright objects, they completely saturate the detectors. So there's bits of hardware built into the CCDs that are positioned kind of halfway along and then halfway along again, and which can be turned on and off automatically on board to limit the integration time for the brighter stars. So for the bright objects, the integration time is 16 milliseconds or something like that. But even that is too long for the very brightest stars in the sky. And the very bright ones swamp the object detection, so instead of a window placed nicely on top of the star, we get some funnies. So all of this we'll have to deal with in time, but these things exist in quite small numbers in the data process.
You mentioned binary atmosphere classification. What's that about? Do you mean the atmosphere of the star to see what the classification of the star is?
Yeah, so the spectroscopic instruments on Gaia look at a very narrow range, spectral range centered on the calcium triplet, which is about 850 nanometers. So there's for F, G and K type stars, which is things that Gaia is tuned to, they have a lot of spectral lines in this range, so that will allow us to classify those stars easily, the ones that are bright enough to be detected in the spectroscopic instruments. Everything else, we've got the blue and the red photometry, which are actually low dispersion spectra, which can be used to get the temperature and spectral type that way. But there's no binary star stuff involved there. Yeah.
Is it, I mean, you mentioned brown dwarfs as well. Did you find more or less brown dwarfs than you expected?
I don't know personally. I think there's only several tens in Gaia data for these two. They're not very bright in optical light. I guess it's possible we might infer the presence of a brown dwarf around a brighter star from the gravitational effects that it has on the primary.
You mentioned exoplanets, and I was curious how those can be detected at all.
Yeah, well, Gaia, there's about 3 methods of detecting exoplanets. Gaia will do 2 of them. So one is the transit method. Planets whose orbits are kind of aligned with our viewing direction will pass across the face of the parent
Is
star.
it able to recognise even if stars in much different magnitude? It's like, oh, I know which star that is. Because there's lots of stars and trying to work out which ones move in which direction. I'm just curious how it can determine a star that has a different magnitude that it's the same star that it saw previously.
So yeah, the cross match is probably one of the biggest challenges. It's just done spatially, so a star that's here, and then the next time we observe it, it's there, and there's nothing else closer. We assume that's the same star, it's moved slightly. That gets very complicated in dense regions. But in terms of exoplanets, each star will be mapped many times, and the brightness occasionally dips when the planet goes in front. And if the orbit's like the other way, so it goes around like that, we see the star wobbling.
Yeah. I can imagine that what we thought were a lot of spectroscopic double stars have actually turned out not to be double stars, they're just a line of sight effect because of the tiny little difference in the parallax that has been detected. Is that true? Is that been...
I think there's was Alberio, is that one of the stars? I think that was recently found by Gaia to be a visual binary rather than
Should we stop and do you want to ask the last question and then we'll get some to
question. Are there any plans, do you know, in a future mission to look at the polarization of the starlight that comes in?
not that I'm aware of, so I think Planck did that. It's not looking at starlight, so...
Because you can tell a lot about magnetic fields by
Yeah, not that I'm aware of. And maybe James Webb has.
Put it in the list for the follow-up question.
Yes, thank you a million. That is absolutely super. It's just such a stunning project. I mean, the stuff that's already released and all the stuff that's still to come is just quite mind-bending. So thank you very, very much for bringing it up to us.
Yeah, thanks for that.